Hi, my name is Andre Workington, and today I will be talking about standards compliance on small and cheap ARM-based single-board computers, such as the Raspberry Pi 4. I'm a software engineer at VMware, and I'm the tech lead for the ESXi-Arm project in the Cloud Platform Business Unit, where we have been porting the ESXi hypervisor, also known as vSphere, to 64-bit ARM platforms. One of the use cases for virtualizing ARM is in virtualizing the far edge, which includes IoT gateways and universal customer premise equipment. I have been working on ARM-based technology for around 10 years, and I have been working on UEFI firmware off and on for about 14. I'm a member of the ARM Innovator Program. My focus is infrastructure. ARM also is one of the stakeholders in this UEFI for Raspberry Pi project. First, we will talk about standard compliance on servers, what these standards are, what they mean. Talk about single board computers and some of the challenges seen there, and how one could go about making the Raspberry Pi standards compliant, if that's even possible. Do a demo and close with a call to action. Now, what is ARM ServerReady? It is what makes ARM servers possible. Both competitive and compatible with the rest of the world, which is, of course, x86-based systems. ServerReady is a blueprint for how you create just works ARM-based infrastructure. ServerReady means adopting existing industry standards around booting, around PCIe Express, around all these aspects of how you build a server, not because they're the best way of going about something, but because it's what the industry generally has decided on. There is a hardware specification called ServerBased System Architecture, SBSA, that tells you how to wire up a machine such that it is an ARM ServerReady compatible server. And there's a boot specification that tells you how to write your firmware, how to hand off state from firmware to OS, and how to boot an operating system. And of course, there's other specifications around management, security. There's an architectural compliance suite, so you can test it to make sure that you can be certified. Now, ServerReady is about making boring infrastructure. Boring in a sense where I can buy an HPE or Dell server today, and I don't have to ask myself whether it will run an operating system that I can also run on my laptop. So that's kind of the definition of boring. Boring means that I don't have to retrain my IT staff. Boring means that you don't need any new skill sets in OEMs or ODMs to design platform solutions around chips. Boring means that software developers can continue doing what it is they do best, and they don't have to completely kind of change the worldview. Boring means that I can have a single ISO of my favorite operating system. Maybe that's FreeBSD, maybe that's Windows. Booting on any one of these machines, at least enough that I can load the right drivers, right? So boring means a horizontally integrated ecosystem. And many in the BSD community will probably chuckle at the idea of standard compliance in ARM because for most of its life, ARM has been anything but compliant. ARM has been a staple of vertically integrated ecosystems. And what this means is that you have some company which rules their own hardware, which rules their own OS, supports the operating system, and rules the entire application stack, and then sells it to somebody. The only thing that company might not do is make their own system on a chip, their own processor. So that's something they will buy from another company. And that other company, because they operate in this specific model, they will provide the board support package for that operating system, but they won't try very hard to create the chip. They'll know that any quirk they have in the hardware can be worked around the software which they'll be providing to the integrator. They can integrate any crazy IP with any quirk, basically. In a horizontally integrated ecosystem, things have to be much tidier, right? I should be able to replace Linux with BSD, Windows with ESX. I can replace one ODM with another, and ideally even move across different CPU vendors without even knowing that I did something special. Again, just like in x86 today. So the server-based system architecture is the spec that guides how hardware is built. It consists of multiple levels. New levels are added as the architecture evolves, and this means including and refining previous levels. Currently, we are at level 6. So what does it standardize on? It standardizes on UARTs, interrupt controllers, IOMMU, how PCIe Express is wired up, how you could add custom peripherals like SATA and USB. What's the right way of doing so? Here's an example. PCIe Express, of course, is cache coherent. Of course, it has to work using ECAM like an x86. You don't need a crazy driver. Of course, by the way, you don't have to configure links. All the programming is done by firmware. All the OS has to do is just use it. There's only one kind of an IOMMU allowed. There's only one kind of interrupt controller. Only one way to do MSI. Only one way to do timers. Only one way to do watchdogs, and so on and so on. A large portion is devoted not just to system level requirements, but to processor requirements around, if you're going to build a server CPU, what should you have? How large should the VMIDs be, right? Should you have RAS facilities and what those are? How do the performance monitoring counters work? So the server-based booting requirement is the firmware spec. This one adopts UEFI and ACPI from x86 world because that's what these modern servers are built with. Of course, not everything can be adopted. There are ARM-specific interfaces, right? A good example of this is the power state coordination interface, which is the way by which an operating system can enable a secondary processor in a generic fashion or disable it. This is implemented on top of, as a bad analogy, some kind of analog of system management mode, right, called trust zone. It's not exactly apples to apples, but it's a pretty good comparison for those of you who might not be necessarily kind of always working on ARM. Okay, so I've talked about servers, but all those non-server devices have always been non-compliant. Even the higher end devices from some vendors are basically treated as high-end embedded. Silicon providers shipping their own versions of Ubuntu, not upstreaming kernel changes or not doing so fast enough, and then kind of dropping off by the time they release a new board. The support for the old board never got fully integrated, right? Doing custom firmware, and that means it's not even, sometimes not even U-boot. Or when they integrate something like U-boot, it's like there's no video, there's no USB support, it's kind of hard to use. So basically nothing off the shelf, tons of vendor lock-in, basically poor support after a few years. This whole class of systems seems like it's well positioned for kind of this new wave of IoT, edge compute, AI, machine learning, but then there's no common ecosystem. Clearly, this is getting in the way of adoption and proliferation. Is there light at the end of the tunnel? I think there is. Clearly, standards are not just for servers. On x86, they're not just for servers. We have laptops, servers. We've seen even some mobile devices built around x86 chips, right? And all of these have one thing in common. That is, the hardware looks consistent more or less to the OS, and what's not consistent is easily described by ACPI and uses standardized firmware to boot. So clearly this could be done on non-server class systems. And in fact, at the ARM TechCon 2019, ARM extended this idea that where you have ServerReady available today, that in some indeterminate future, you could have related profiles for client devices such as laptops, for edge devices such as IoT gateways, for smart NICs, and all of these would maybe share like 90% of what goes into a server. Of course, there'll be differences simply because of the different kinds of use case or requirement. Like you can imagine low power mode is very, and kind of going to sleep and coming back is very important for a laptop, but not so important for a server. So at a high level, this is happening, this understanding that it's not just servers that stand to benefit from standardization. Many of you may have heard about EBBR. EBBR is the embedded base boot requirements, but this spec really standardized on the idea of using UEFI-like firmware interfaces to hand off to the OS. It doesn't tell you exactly, first of all, how the system should be built. That is completely open. And it also doesn't really describe what that handoff state from firmware to the OS is. So most likely it's going to be device tray, right? It can be a CPI, right? So a good example, a Raspberry Pi that uses third-party U-boot, that's EBBR, right? U-boot can run the UEFI OS loader like Grub, pass it the device tree, and OS can use it. Another example, which some may disagree, but the always connected Windows PCs, which run Windows 10, like the HP Envy or Lenovo Yoga, those are also EBBR devices, except they use ACPI, they don't use device tree. But they're not really SBSA, SBBR. In fact, you need a custom OS image to boot on the laptop, Windows or Linux. So that basically means it's still really that EBBR mode where you have to run an OS tailored to the hardware, even though you may have standardized on some portion of that boot flow. Okay, so what can we do about this? Well, why don't we take the most popular platform in the world, that's ARM-based, and try to make it standards compliant. So that could be a Raspberry Pi 4. It's a high volume, low cost device, only $50. Clearly usable by everybody. You can buy it anywhere. There are folks out there who haven't heard about ARM, but have heard about the Raspberry Pi. Now, one of the advantages about targeting the Pi instead of some other board is that the Pi will be around, right? There's a Pi 4, there'll probably be a Pi 5, and by the time folks are using Pi 6, you'll still be able to use a Pi 1, right? So the Raspberry Pi Foundation has created a vertically integrated ecosystem, right? But either because it has some good approach about it or because they were the first there, they have created a vibrant ecosystem. I would say that it's a place where other SBC vendors can't really compete because they're not providing any value, right? So with a Raspberry Pi, you could be locked in to their software stack, right, and to the hardware, but at least you know you'll be able to use it in 10 years. And you have a massive community of software and hardware hackers to kind of pull on. With all these other SBCs, well, yeah, there's like some half-baked support today, and then 2 years is just a paperweight. So if somebody wants to compete with a Pi, I would suggest going and looking at making solutions which are interoperable, which are compatible, and which follow this idea of standards compliance. But in our case, since we're just starting to kind of get this ball rolling, let's go for that most popular board, and that's the Raspberry Pi 4. Now, is it feasible? You clearly could not do this with the Pi 3 because the Pi 3 didn't have a standardized interrupt controller. Now, the Pi 4 has a GIC v2 that's not part of, say, level 6 because level 6 already mandates GIC v3. But the Pi 4 only has 4 cores, so yeah, GIC v2. If you cap your compliance level, let's say 2 or 3, it should still be at least compliant to that. It has proper USB 3, wired up using some fairly improper PCIe Express, but we can pretty much ignore PCIe Express because there's no physical slot. You cannot plug in, well, you can solder, and we've seen that somebody actually did a cute hack. But for most of us, we're not going to be attaching our Mellanox NICs to a Raspberry Pi 4. And so by that stretch, it doesn't matter if the OS sees PCI Express or it doesn't. So as long as we can just expose the USB 3, if we can configure it and make it presentable, okay, great. If we were to do this project, how should we do it? Of course, we should do it out in the open. Should be a true open source project. Of course, set an example and show others how it could be done. Now, there are folks in the audience who don't care about IoT, don't care about small board computers, and might actually not really like the Raspberry Pi. Why would any of you care? Well, because there are no good client platforms today to build a good mass of developers. If I want folks to build from my Xeon A7, they can do it on a $200 laptop. If I want somebody to build for a Thunder X3 whenever that comes out, what am I going to use? So maybe some of the cloud vendors have been partially solving this problem, but in general, in order to build kind of real momentum, you need small devices in the hands of developers, something approachable. In the ARM server space, people have been lamenting the lack of approachable hardware. By approachable, I mean cheaper than $500. So the Pi could do it, right? I mean, it's not a server, that's kind of obvious, but you can do OS bring up, you can do some work on bootloaders, driver bring up, and actually validate a lot of, or clear out a lot of assumptions in system software, right, around supporting ARM or cleaning up architecture dependencies. So why not? And if we had the SBBR, SBSA, or something at least 90% of compliance, you could boot Red Hat, you could boot Windows. That would be kind of cool, right? Red Hat obviously is a product today. Windows isn't commercially available unless you buy a Windows on ARM laptop. You can clearly boot all those EBBR operating systems available today for Raspberry Pi, such as SUSE, Ubuntu, Debian, NetBSD, FreeBSD, OpenBSD. That's kind of cool. And clearly, if you had an ACPI OS that was still tailored to the hardware, a good example of this is NetBSD booting on the Raspberry Pi 3 in the UEFI mode, then yeah, sure, you could do that too. So, having these thoughts, we basically got this project going. Now, this project really is an evolution of the early work done on the Raspberry Pi 3. It all started way back when Microsoft released the 32-bit UEFI sources for Pi 2 and 3 as part of the Windows IoT Core. At the same time, one of the Linaro developers, ARD, published a very minimal 64-bit UEFI for the Raspberry Pi 3. And this was a very important step to even beginning with a 64-bit port. And the way it was done, it was kind of done correctly. It used this trusted firmware aspect for PCIe, so you could properly enable cores without using some weird mailbox hacks. And I looked at these two things and got excited, and I thought it'd be great to kind of mush it all together and get some drivers inside ARD's firmware. It didn't end up being a walk in the park, but hey, we got USB going. Video, SD cards, and it started looking like a pretty usable system. It was capable of booting SUSE Linux, OpenSUSE, which is pretty cool, of course, using device tree. And then folks started challenging me to make Windows bootable. I thought it was completely impossible, but kind of one thing led to another, and we could show that, yeah, Windows was actually booting on the Raspberry Pi 3. Again, mostly courtesy of all the work that Microsoft has done to get Windows to boot on the Pi 2, and just that code stayed around in their 64-bit builds, but still. Then I actually demonstrated ESXi running on the Raspberry Pi 3 at one of our VMware events. And then a gentleman by the name of P. Bartard graciously decided to upstream this code, which just sat around GitHub, to upstream it to proper Tiano core, which is the upstream for UEFI firmware. Tiano EDK2 being Intel's reference implementation of UEFI. And it was a pretty monumental effort. There was a ton of rewrites that happened along the way before the code was allowed to be merged in. But what this meant is that by summer of 2019, anybody could go check out the Tiano Core UEFI and build it and run it on the Raspberry Pi 3. Now this is where the Raspberry Pi 4 came out, and between VMware and ARM started talking about it, and we decided that it'd be cool to go and add Raspberry Pi 4 support with Pi 3 codebase, and why not try to make it standards compliant? And one thing led to another, and I demonstrated ESXi-Arm at the ARM TechCon running in the Raspberry Pi 4. ARM developers, including Jeremy Linton, did a number of contributions, such as the UEFI driver for PCIe Express, which meant we had working USB 3. The first kind of official 1.0 came out in December, and we could boot Linux and NetBSD using ACPI with a working USB. As of right now, we just got native networking, gigabit networking working inside UEFI, courtesy of Jared McNeil, who ported his NetBSD driver to UEFI. So now you can do HTTP boot. You do not need any USB dongles. It's very cool. So this Pi 4 firmware task force right now comprises, it's all kind of volunteers. It's the project got started by ARM and VMware, but it really is a community project. There are developers from VMware, from ARM. Pete has his own consulting company, and Jared, of course, works on NetBSD. Everything we do upstream. But of course, we have our own staging branches, and these are available on GitHub as well. Everything is kept up to date with upstream. Now, the Pi 4 code is inherently an evolution of Pi 3. There's a lot of commonalities, and so we do produce Pi 3 builds as well. So that's not standard compliant, of course, to SBSA and SBBR, but it's still useful for somebody, right? We have a bug tracker that we pretty actively use. We try to run those ACS test reports to see how far away we are from standards compliance nirvana. Releases are available exactly where you see them on this link, and there's an official blog, rpi4-uefi.dev, where you have news, blog articles, that sort of thing. So here's an example of that blog. You can kind of read about in a more cohesive fashion about why should we make the Pi be standards compliance, and you can look at the status reports and read about releases. Actually, very importantly, there's a link to our Discord channel, rpi4-uefi-dev. This is on ARM's Discord server, which is an ARM developer-oriented server. There's tons of topics, all ARM-centered, but with very different focus areas. Pi, Windows and ARM, works in ARM. You've got different silicon vendors there. You got ODMs. You can talk about microcontrollers, IoT, pretty much anything that involves ARM is fair game on that server. Okay, so what do we have today? We have actually quite a bit, a fairly reasonable system that somebody who's not a UEFI developer could go and do something interesting with it. Okay, so we support both UART devices. We support a video console, USB devices, including both the front ports and the Type-C port, which is a custom USB controller. Support removable media using the SD host controllers. We emulate NVRAM. It's just file backed, but with a file on the SD card. We even have a random number generator, and of course now we have a native UEFI gigabit driver, which I think is pretty amazing. We implement trusted firmware, as of course a compliant system should. We implement operations to enable CPUs, disable CPUs, and of course reset and power off the hardware. We do not implement the NMI interface yet. That's this SDEI, the software delegated exception interface. And this is how you could implement proper NMIs on ARM hardware today, which don't support NMIs in hardware. Some other cool things is this is the only way by which you could do pixie booting on the Raspberry Pi, or use iSCSI, or boot using HTTP. We use SMBIOS to communicate sort of inventory. Of course, we have very early ACPI support, which today just describes USB and networking. And we have EBBR compliance in the sense that we just expose the device tree that the firmware, that the GPU firmware gives us. And this includes overlays. So for those of you familiar with using config.txt and DTBO files to match whatever Raspberry Pi had, all of that works, right? You can still do it. Now, the goal of this project is not to create some kind of academic firmware which, by throwing away 90% of the board functionality, you can kind of claim success. So today with ACPI, yes, we're only exposing USB and networking. Actually, we're also exporting the SD host controller, at least one of them. But more devices should be possible. In fact, we expose much more, but as far as OS support for those, for example, in Linux, it's non-existent. Nobody's done that work. Within NetBSD and OpenBSD today are probably the best operating systems in terms of support for the platform using ACPI bindings. So some of the biggest challenges is in the way how USB is wired up. Due to a silicon bug, the PCIe Express root complex can only address 3 gigabytes. Well, the Raspberry Pi comes in a 4 gigabyte flavor. Because of that, there needs to be a way by which the firmware can communicate to the operating system that it shouldn't use the full 4 gigabytes for DMA. Fortunately, there is a way. Another interesting issue is that what I would call the legacy devices, so these are devices that are shared with the Pi 3. These are the ones that are behind the video core GPU. These have a 1 gigabyte DMA limit, and they have a translation. So translation means that the CPU addresses and the bus addresses aren't the same. Now, none of this violates the specifications, but nobody has done anything like that or talked about it. So there's quite a bit of impedance mismatch with sort of like, does any existing operating system support this that is still server compliant? Okay, so there were two thoughts about exposing USB. One was, could we expose PCIe Express? And the short answer is no. Wrong alignment, and it's not cache coherent. And if that's not enough, you can't actually scan anywhere past bus 0, device 0, function 0, because there are other registers, unrelated registers following that. So you'll just read garbage and or crash, kind of depending on what OS you're in. So that wasn't a great idea. What else could you do? Well, I mean, clearly you could virtualize, right? But of course, I work at VMware. I didn't want to have only EL1, that's kernel mode, available on the Raspberry Pi. I wanted to have something generic enough where you could still run a hypervisor, and folks wanting to run KVM or Hyper-V, why not, right? Okay, so we don't want to virtualize to high PCI Express quirks, and we can't expose PCI Express directly. Well, like I mentioned, we don't actually need PCI Express because there's no physical slot. Could we just expose the USB? Yes, we can. So this idea is that the UEFI configures PCI Express. It assigns resources to the base address registers for the PCI device. And then we make sure that the DSDT, the ACPI definition for the USB device, just has the right addresses in it, right? Folks that are not familiar with ACPI, ACPI basically is like device tree, except that it's written in a bytecode. And I'm not talking about the static tables, but the main section of ACPI that talks about the hierarchical devices is a lot like device tree, except it's written in a bytecode, and everything you evaluate is basically a method. So you can do things at a runtime. Okay, some interesting challenge. UEFI actually disables bus mastering on the way out, and we need to somehow enable that. Well, fortunately, there is this concept of an initialization method that the OS ACPI interpreter has to run. So on the example on the right, you can see that that's kind of what we did, right? We defined an operation region, which is just a way by which ACPI bytecode can do I/O to system memory in this case, and we just go and we blast the write into that field and make sure that sets the command register for the device to make sure it can do DMA. And this CRS stuff, that's just how resources are reported to the operating system. So here you see we define a range which corresponds to the one bar that the USB controller has. And we define the interrupt which corresponds to the level interrupt int A for the PCIe Express device. Okay, well, that will make USB work on a 1 gig board and a 2 gig board. So what about a 3 gig board? Sorry, a 4 gig board. Well, that's where you have this problem with how do you describe the DMA range. In device tree, there's an easy way to do it. In ACPI, there is one as well. The way you do it is you take your USB object, USB controller object, and you nest it under another bus controller object. In this case, it has this funky harbor ID of ACPI 0004. It's a container device, and container devices can have DMA resources, and a DMA resource is what can do the remapping or provide the custom range. So it's in a spec, right? But the ACPI spec is pretty large. Not everything in the spec is actually implemented by folks. In particular, in Linux, there's no support for this outside of some corner case for the PCIe Express root complex and how it integrates with ACPI. Thanks to Jared McNeil, NetBSD is probably the first OS on the planet to properly decode and support this. And Jared went all the way and not just made the limits work, but made translation work as well. So all those legacy devices that I kept talking about that have the only 1 gig limit and then have the 3 gigabyte translation, yeah, those work in NetBSD as well. There was like a fine line patch to Linux that seemed like it could make USB mass storage work, but there's probably more work still necessary there, either to enable some kind of bounce buffering or to properly propagate the DMA limits, because other USB devices like HID or networking didn't work with basic control transfers failing, implying that the wrong addresses were being passed around. Okay, as far as Windows, my understanding is Windows doesn't support DMA resources either. Okay, so kind of in light of this, we did introduce this kind of ACPI boot profile that limits useful RAM to 3 gigs. You can turn this off and get your full 4 gigs back, but if you boot an OS that doesn't support, yeah, you can cap your RAM to 3 gigabytes. It's not ideal, but it's something. Well, what if you don't have a Raspberry Pi 4? Can you enjoy this UEFI party and do interesting things and use this as a development for UEFI maybe? Development for UEFI bootloaders, applications? Yes, you can, right? Maybe you want to be able to use Pixie booting or use iPixie, but don't have a Raspberry Pi 4. So the good news is, again, like we mentioned, we still make Raspberry Pi 3 releases. We still actively maintain that code because it really is the same code as the Raspberry Pi 4. And actually, very recently, I added support for both Raspberry Pi 2, the 64-bit variant of that. Yes, there was one. It's a revision of 1.2. They basically ran out of the 32-bit chips, and they started putting the 64-bit ones on. So that's the Pi 2 Model B Rev 1.2. Also, Compute Module 3, 3 Plus should work as well. And of course, the diminutive Model 3A Plus with only half a gig of RAM. All these are supported with the Raspberry Pi 3 image. Whew, okay, now a brief demo. Here's some funny static pictures. That's Windows booting all the way to setup, but of course no input. But folks have actually managed to use The USB controller driver from the Raspberry Pi 3, that's only Type C for the Raspberry Pi 4. As long as you cap your RAM to 1 gig, you can actually get a fairly decent Windows experience. Here you see a development screenshot of ESXi running on the Raspberry Pi 4. And of course some pictures of functionality like working PCIe Express inside UEFI, enumerating the USB controller. Okay, but here, what I have here, I can show you real OpenBSD, booting on, of course, the Raspberry Pi 4. So let's take a look at that. So this, I believe, is actually booting using device tree mode, which OpenBSD actually supports booting using both the device tree and a CPI. And what I'm going to show you is both ways. So I will show you it booting up into OpenBSD, and then I will log in and I will reboot, and we're going to set it to boot in the other mode, and we'll see it boot again. OpenBSD is the only OS today that's capable of this feat on the Raspberry Pi 4. Although NetBSD should be possible with NetBSD as well. So allow me to log in. Okay, so just in case this is all fake, it's not. ARM64, OpenBSD. All right, let's reboot. It's funny how if you're not showing a demo, it feels like it's much faster. So I'm going to mash the escape key to get into the UEFI setup. Here I am, right? So this is pretty normal for Tano Core. What can we do here? We can set the console preference. Serial means that if I had a serial dongle connected, then the serial port will be exposed over ACPI as well. You can set it to graphical, in which case you will not get a serial port available to you that way, and you will not be able to interact with it with serial. A booted ACPI OS. You can do RAM disk. Raspberry Pi configuration is where some of the interesting stuff is. You can set the CPU clock rate here, right? The default would be like 1500. Max, I guess, is the max that you can do. Display. This uses basically this concept of virtual resolutions. So in this case, I set it to 800 by 600 just so you can have a decent picture. Usually it's only set to native resolution, and then you'll just see whatever the native resolution is. This actually works the other way back too. So let's say you have your Raspberry Pi 4 connected to like a TV using SDTV. You can pretend that you have 1080p, right? Even though you don't, right? You'll get a very fuzzy picture, but so it can scale up and scale down. But it's still better than nothing. Okay. Let's not mess with that. But advanced config is here. This is where you could set the limit to 3 gigabytes, right? I don't. I want the full 4 gigs. And this is where the system table selection right now was set to device tree. So only device tree was exposed to the OS. I can expose both and let the OS figure out which one it wants to use. Let's set it to ACPI. Okay. There's some options around like some debugging settings for the SD host controller. Again, some debugging options available if you want to play around with it. Okay, so yes, we want to save. Configuration for iSCSI, network device list. This is where you can set up HTTP boot, right? Very cool. This is using the GNet onboard SoC. NIC. Okay, so we're gonna have to reboot, have to reset to apply the new settings. And now let's boot OpenBSD again. And now we see that it's actually using ACPI, right? So it's booting exactly using ACPI. You get the same experience, right? You get working USB. You get, I believe in ACPI mode it doesn't support the SD host controller yet. But these are just details, right? Okay. So now I guess is the call to action. Like I mentioned, it would be fantastic to have more device bindings for the Raspberry Pi 4 using ACPI way of bindings, like GPIO controllers, I2C, SPI, that thing, right? We have the devices exposed, but folks need to adjust the drivers. We're looking for more help on the UE5 firmware front. There's always things to do. We want to support the new SD host controller. We would like to make the firmware kind of configure itself using the device tree that's passed by the GPU firmware, for example. Hang out with us on our Discord server channel. Ask us questions. We'll help you get your OS up if it's not running yet. We've had NetBSD, OpenBSD developers hang out there, some FreeBSD developers as well. You're welcome to contact me directly on email. You can also contact my ARM counterpart. His name is Samar El-Haj Mahmoud. He's a principal at ARM focusing on standards. Now, Raspberry Pis are great, that's cool, but there are other interesting platforms. Obviously, NVIDIA being a high-end platform, it would be fantastic to make that thing standards compliant, right? Also, Rockchip-based platforms, because they're so well documented, you get the documentation available without an NDA. Pinebook Pro uses the RK3399. It would be amazing to have a standards compliant laptop. I actually have a work in progress UE5 implementation for the RK3399, but unfortunately I have very limited resources. I'm not working on that right now. UE5 doesn't have to be Taino Core. Taino Core, of course, is the BSD license implementation that is now a community project and was started by Intel. But that's U-boot, and I'm sure there's other implementations out there as well. Let's make them all work with ACPI, expose ACPI to the OS. For those of you not on this, please join the ARM Server Advisory Council. Reach out to me if you would like your OS to be represented there, or if you want your silicon vendor provider be represented there and you're not yet, and I'll connect you to the right folks. Yeah, let's work together. Let's shape the standards and the requirements for non-server systems, right? Clearly, there's a lot of overlap with servers, but there's things that have to be solved, right? Okay, so thanks a lot for your time, and I'm looking forward to your questions. Thank you.